Underwater nuclear explosions, such as the Wahoo shot of Operation Hardtack, are capable of producing extensive water wave systems that can inundate nearby land masses. Accordingly, the possibility that wave run-up and inundation could cause extensive damage to near-shore facilities makes the study of wave run-up phenomena mandatory. The waves, the run-up, and inundation effects resulting from Wahoo are impressive, particularly when it is considered that the shot was positioned at a submergence depth that was not conducive to the generation of water surface waves. Thus, in an effort to better understand explosion-generated waves and their run-up on shore, a series of 10 large-scale underwater explosions was conducted at Mono Lake, California. The objectives of these tests were to study surface wave generation as a function of charge depth, to study wave propagation in deep, intermediate, and shallow water, and to evaluate wave run-up on beaches of various slopes. The Defense Atomic Support Agency authorized the Mono Lake tests and furnished the necessary funds. The Office of Naval Research managed and administered the overall program, while the U.S. Army Engineer Waterways Experiment Station planned and executed the test series. Other participating organizations were National Engineering Science Company, URS Incorporated, Scripps Institution of Oceanography, Oceanographic Services Incorporated, and the U.S. Coast and Geodetic Survey. Mono Lake is located on the eastern side of the Sierra Nevada mountains due east of Yosemite National Park, 110 air miles south of Reno and 180 miles east of San Francisco. The lake is roughly 10 by 15 miles and covers an area of about 85 square miles. In the central portion of the lake are two islands, Peoha and Negat. The lake is fed by chemically laden springs and has no outlet other than evaporation, which is considerable in the arid climate of this region. Because of these factors, it is extremely saline and is inhabited only by tiny brine shrimp that average 3/4 of an inch in length. It is also the breeding place of the Ephida fly. In the Mono Lake tests, it was desirous to study wave run-up common to bottom and beach slopes that were representative of continental shelf slopes. While the eastern end of Mono Lake met this criteria, the beach area in this region was too soft and quicksand too common to permit vehicular movement. The south end of the lake was selected for the operation, although the bottom and beach slopes in this region were only 1/30. Somewhat steeper than the continental shelves, but sufficiently flat to provide quantitative data that could be used with the aid of existing theories to infer what the run-up would be for flatter slopes. In order to have access to this section of the lake shore, it was necessary to construct approximately 2½ miles of road, an operations area on the beach, a boat docking facility, and a charge loading ramp. The Naval Ammunition Depot of Hawthorne, Nevada constructed most of these facilities and furnished heavy equipment and numerous support items during build-up and execution of the project. Because of the shallow water in the test area, an approach channel to the boat docking facility was necessary. To accomplish this, 5 300-pound charges were positioned on the lake bottom in a straight line 17 feet apart. All charges were detonated simultaneously. The resulting channel was about 8 feet deep along its center line. In spite of several windstorms that produced 1 to 2 foot waves, the channel was still 7 feet deep 3 months later. Buildup of the operations area included spotting of support and storage type vans and trailers, construction of temporary shelters, installation of the water supply, wiring and cable hookup for electric power, modification of certain vehicles to permit mobility on the beach, erection of a WWV radio antenna for accurate timing of all detonations, and construction of the 50-foot camera towers. To avoid excessive energy losses during the wave run-up process due to abnormally high frictional forces and percolation into porous sands of the beach, 2 impervious beach slopes called run-up decks were constructed on slopes of 1 on 50 and 1 on 30. The run-up decks were constructed of 2x4 stringers and covered with 1/2-inch plywood sheets. Staff gauges were positioned along the center line of each deck. These run-up decks were located about 1,800 feet apart along the south shore of the lake. A camera tower was positioned near each deck. The first 9 shots were fired at a surface zero 4,700 feet from shore. The final shot of the series was fired at a surface zero 3,000 feet from shore. Wave gauges were positioned along 4 radials. Number 1 was essentially perpendicular to the beach. Number 2 intersected the shoreline at an angle of 15 degrees. Number 3 was oriented at an angle of about 30 degrees. And number 4, the deep water radial, was directed generally eastward so that all gauges in this radial were in a near constant water depth of 130 feet. Shallow water gauges were supported by iron pipes driven into the lake bottom. All deep water gauges were supported by spar buoys. The buoys were fabricated from a length of 2-inch pipe positioned in the center of a sheet metal cylinder filled with styrofoam. A length of pipe attached to the upper end of the spar buoy provided for the mounting of a wave gauge once the buoy was anchored in position. A 1/8-inch steel cable was threaded through the center pipe. The cable was then connected to a small winch, which was mounted on top of the pipe above the flotation cylinder. To prevent bobbing and objectionable oscillation of a given buoy, 1 or more cylinders could be coupled in series for increased buoyancy. The lower end of the cable was attached to a concrete anchor, which was gradually lowered to the lake bottom. As the anchor was lowered, the buoy righted itself. The entire assembly was raised or lowered by means of the winch until the water surface was about midway of the gauge support pipe. Plastic-coated signal cables were run to each location and connected to parallel wire, variable resistance type wave gauges. Facilities for automatically calibrating each gauge completed the installation. A charge flotation device was designed for the monolake tests, which provided positive charge positioning, yet offered no noticeable interference to bubble or cavity formation. Prior to construction of prototype components, the efficacy of this type of charge flotation rig was verified by 1/10 and 1/4 scale models at WES. The device consisted of a tripod arrangement that rested on top of 3 flotation pads. The flotation pads were 7 1/2 feet in diameter and 30 inches high. The tops and bottoms of the pads were made of laminated plywood. The sides were sheet metal skirts. Each flotation pad was filled with styrofoam to ensure positive and effective buoyancy. The legs of the tripod were made of 5 by 10-inch timbers, 18 feet in length, and joined at the top by a metal framework. The ends of the 3 legs formed the vertices of an equilateral triangle 12 feet on a side. A wooden platform placed near the top of the flotation device provided space for operating a 15-ton capacity winch used to raise and lower the explosive charges. The Naval Ammunition Depot, Hawthorne, Nevada, cast the 5-ton spherical charges used during the tests. The lower half of the fiberglass mold was recessed to receive an especially constructed nylon sling that provided a means of handling the charge once casting operations were completed. Molten and solid chunks of TNT were poured and placed into the bottom half of the mold. A removable wooden core was positioned so that its center would correspond to the center of the finished spherical charge and provide spacing for the booster. After the lower half had cooled, an 85-pound pentolite booster was placed in the nesting cavity. The top half of the fiberglass mold was thoroughly lubricated and secured to the lower half. The conically shaped arming port was positioned. Then pouring operations were resumed. After curing, the charges were delivered to the Mono Lake test site and offloaded at the charge loading ramp. The upper half of the shipping container was removed and the lifting straps attached to the crane hook. The charge was lifted from the container and placed in the water. The flotation rig was floated into position astraddle the charge. A non-rotating cable was securely attached, the charge lifted from the bottom, and the entire device towed to the surface zero area and anchored in position. The lateral positioning of each charge was controlled from triangulation survey points about 1.5 miles apart on the south shore of the lake. The lateral error in positioning was never in excess of 2 feet. In arming the 5-ton charges, each detonator cap was first subjected to a continuity check. Its connecting wires threaded through a cone-shaped pentolite booster and the cap seated in the smaller end. A conically shaped wooden dowel pin that protected the arming port was removed, and the pentolite booster eased into position. A second continuity check of the firing line preceded the series connection of detonator leads and the firing line. The demolition officer and his arming party returned to the beach and last-minute preparations continued. At H-30 minutes, all personnel moved to their assigned stations. At -20 minutes, the calibration of wave measuring devices was initiated. H-15 minutes. All high-speed and conventional motion picture cameras had been loaded, checked for proper exposure, framing rates, and coverage, followed by a quick check of the beach and lake areas. 5 minutes. Check wind speed and direction. 3 minutes. Complete safety check and close firing circuit. 1 minute. Automatic counting and firing control initiated. One shot was fired with the charge center of gravity 1 400 feet below the surface. This was filmed at 500 frames per second from a tower approximately 2 miles from surface zero. Camera towers were nearly 90 degrees apart to aid in resolving any explosion asymmetries. This shot was fired with the charge center of gravity 21 feet below the water surface. Photographed at 500 frames per second, the camera was 2 miles from surface zero. The upper and lower critical charge submergence depths observed at small scale exist at the 10,000-pound level also. The lower critical depth was shallower than predicted by extrapolating the results of earlier small-scale tests. The scaling of the upper critical depth was found to be consistent among all charge weights for which comparisons are possible. The lower critical depth scaling is apparently sensitive to gravity effects which modify generation mechanisms. Another shot was fired with the charge center of gravity positioned at the surface. These scenes were photographed at 64 frames per second from behind the first run-up deck. Wave generation and propagation phenomena in deep water agree with earlier small-scale tests and with those elements of the theory that have thus far been examined. The region wherein wave form was modified by shoaling phenomenon was well documented. These data will aid substantially in formulating the shoal characteristics of explosion-generated waves. Run-up of explosion-generated waves over flat slopes was fairly well predicted by theory and by conventional wind wave run-up charts. Run-up was about 10% greater on the 1 on 30 deck than on the 1 on 50 deck. Wave run-up observed in the Mono Lake test indicates that almost all of the higher waves in the train tend to break at rather large distances from shore when the slopes are 1 on 30 or flatter, thus greatly reducing their run-up potential. This effect was offset to some extent by the cumulative increase in the water level near shore due to the mass transport of water into the surf zone. More detailed and rigorous analysis is needed before the potential hazard from such effects can be satisfactorily estimated.